What is this mechanical advantage? Mechanical advantage, or abbreviatedly MA, is defined to be the ratio of output force to input force. So as we said in the previous session, output force is also called resistance or load, which is denoted by R, and input force or effort is usually denoted by E. So mechanical advantage is equal to resistance over effort, or load over the force applied. Okay, when there is no loss of energy or there is no friction, we can assume that R times dr is equal to E times dE, which is the input force is equal to the output force, or the work done by ourselves is the net work done on the system. So because there is no loss of energy, we can assume this. And therefore, mechanical advantage can be written as R over E is equal to D over dr. Okay, this formula helps us to, in many cases, to calculate the mechanical advantage of simple machines. For example, in an inclined plane, we apply the force in an inclined plane. We apply the force here. So this is E, or effort. But in fact, we want to raise this mass from here to here. So this is the distance which the load will be. We want to change the load, and this is the distance that the force will be applied. So if I show it by some arrow like this, this will be dr, and this will be dE. And therefore, based on the formula we have just developed for mechanical advantage, it is equal to R over E, or dE over dr. dE over dr is the reverse of sine of theta, because sine of theta is defined to be the opposite side over hypotenuse. So therefore, hypotenuse over opposite side will be the reverse of sine. Okay, this is mechanical advantage of an inclined plane. What about levers? Okay, we had three types of lever, as you remember. In the first type of lever, the fulcrum was in the middle. We have load here and we have effort here. Okay, we learned in the equilibrium, we learned in the 8th session about one of the equilibrium condition, which was the resultant torque must be equal to 0. And therefore, so if I call this distance, we call the distance between the load and the fulcrum to be called load arm or resistance arm. So let me show it by LR. This is called resistance arm. This is called the resistance arm or load arm, which is a distance between this force and the turning point or pivot point. At the opposite side, the distance between where we apply effort to the fulcrum is called LE, or it is called effort arm. Or effort arm is the best. Okay, so effort arm. So now effort applied to this beam causes counterclockwise torque. So we can write E times dE is equal to R times dr, R times LR. So instead of L load, I'm writing R as over resistance, no matter. Okay, therefore we wanted to know what is R over E, and therefore based on the cross multiplication we can write dE, I need to write here LE, which is the effort arm. It is different from distance that the effort moves. It is different. For example, if this beam moves down here, this will be the DE and this will be the DR if it turns a bit. Okay, so if I want to correct it here, it will be LE, or effort arm, over the resistance arm. This is the mechanical advantage of a lever type 1. The same formula applies for levers of type 2 and 3. Let's see what happens here. Here is a load. This is lever type 2. In lever type 2, load was in the middle. And of course, this direction of E is incorrect, because if both E and L is downward, we'll have no we'll have no clockwise torque. Of course, the direction here is the direction here must be toward the up here. So to keep this load in balance, or to keep it's like a wheelbarrow, lever type 2. So in order to keep this lever balanced, we need to apply a force upward. Okay, now again, the distance between the effort and the fulcrum is called effort arm, and the distance between the load and the fulcrum is called load arm. So this is L of R and this is L of E. I'm replacing the load with resistance R. Okay, therefore again we can say E times DE, E times LE is equal to R times LR, and therefore R over E is equal to effort arm over resistance arm. This is defined to be the mechanical advantage of type 2 lever. It is clear that LE is greater than LR. Therefore, in type 2 lever, mechanical advantage is always greater than 1. So when mechanical advantage is greater than 1, it says R is greater than E. So we can overcome a greater force with less effort. Therefore, it is good for us. That's why it's called advantage, mechanical advantage. In the lever type 1, we cannot say if it is bigger than 1 or less than 1 or equal to 1. It is based on the length of LR and LE. If fulcrum is exactly in the middle, then mechanical advantage is 1. Of course, this type of machine again help us in a way that the direction of the force changes. For example, we want to bring up something and then we apply the force downward. It's this simple machine. Even if the mechanical advantage is 1, it helps us in a change of direction of the force. Okay. In the third type of lever, again I need to correct this direction to keep the balance of this beam, or to keep the balance of this lever. I need to apply the force upward. So again, we can say the distance between the lever. We can say the distance between the fulcrum and the effort is LE, and the distance between the fulcrum and the load is LR. Okay, so this is LR, this is load or resistance, this is LE or effort arm. Again the same formula, but this time, because LE is less than LR, mechanical advantage in lever type 3 is always less than 1, which means we apply more force to overcome a resistance. But this more force is instead of we apply more force, but instead less distance. We cover less distance, and a large distance will be given to us. Okay, let's go over a fixed pulley and see what is the mechanical advantage of fixed pulley. Okay, so it is clear that this is the effort and this is the load or resistance. Because we have a thread or a string here, dE and dR are equal to each other. I mean, when we pull this down 20 centimeter, this goes up 20 centimeter. Therefore, dE and dR are equal to each other, and mechanical advantage is 1. Of course, when there is no friction, mechanical advantage is 1 in a fixed pulley. In a movable pulley, it is like this. By the way, in a fixed pulley, we can think of it like type 1 lever. If you think of a lever like this, and this is the fulcrum here, which is not moving, you apply the force downward and you're bringing up some load. So it's like a fixed pulley with mechanical advantage of 1, where the effort arm is equal to the load arm. In movable pulley, again we can say this point is fixed at this moment. When we bring up this string, this point is fixed at this moment. So we can say it's like a lever type 2, that where the load is in the middle, the effort is here, and here we have the arm. Effort arm is double the resistance arm. Therefore, the mechanical advantage is 2. Okay, it is clear. Another way we can think of this in another way. For example, we can say how this load will be in balance. This is sustaining in equilibrium condition. A sigma F must be 0, or resultant force must be 0, and resultant torque must be 0. Okay, now this pulley and the load is hanging on the air. The weight of the pulley is negligible. So this weight or load must be kept up by 2 forces. This is one force. The tension of the spring, the tension in the string is called T or E. Here effort is the same thing. So here we have E, here we have E, and therefore 2 upward forces, 2E cancels 1R, and therefore R over E is 2, which says the mechanical advantage of the mechanical advantage of a movable or moving pulley is 2.